Thank you, Dr. Agumbiade. Good morning, all. Apologies for the late commencement. We had a couple of things to sort out quickly. Can we do a quick sound check? Can someone let me know if you can hear me?
Yes, they can hear you, sir.
We can hear you, sir.
Thank you very much. Thank you very much. My name is Dr. Izunobi. Today, we're going to be continuing with this section of your class, CHM 121, the organic section. Can I appeal that you stop typing and sending in your attendance, because you're going to be disturbing the class. So, Professor Adams kicked off the organic chemistry section of this course. Previously, you have had 3 other sections, physical 1 and 2, and inorganic. And then now you're in the organic section. No need reminding you that you're going to be having a test covering sections 3 and 4. So today we want to look at carbonyl compounds. Professor Adams continued in your year 1, you were introduced to the rudiments of organic chemistry. Most of the things you would have come across are things you were taught in your secondary schools that you needed to know to come into the university. This part of the course is a continuation. So Professor Adams would have kicked off by telling you about phenols, ethers, and alcohols. And what you would notice is that these different grades of compounds are characterized by what we call their functional groups, the combination of elements that bestows on them certain properties. You come out, if you're a male or a female, there are certain things that males can do that females cannot do, and vice versa. So usually, you would pick out a human being and categorize them into male or female, depending on those characteristics that they exhibit. So you've come across alcohols which have a functional group OH, generally represented as ROH, where the R can be an aliphatic or aromatic substituent. Then you went ahead to talk about the ethers, RO prime, ROR prime. Then, so today we're going to be looking at the carbonyls. The carbonyls, Dr. Agubiade, please, can you, is there any way you can stop these students from, some of them are just here to type in their names. Okay, so today we're going to be looking at carbonyl compounds. Carbonyl compounds are characterized by the functional group of carbon bonded to oxygen with double bond. As you can see here on the slide. Okay, and there are 2 main types of carbonyls. So usually we say that carbonyls are represented by the general formula of RCOO, and here R prime. R prime is used to differentiate the other R. Sometimes they can be the same. Most times they are different. Okay, so there are 2 types. When this R is equal to H, they are called aldehydes. But when the R is not H and is other substituents like aliphatic groups, methyl, ethyl, or aromatic groups, phenyl, and all the rest, we call them ketones. So those are the ones we're going to be looking at today. And the main characteristic of these compounds is their possession of this carbon-oxygen double bond and The difference will be in their R prime. One is H, and the other one is is organic, R. So carbon atoms in the carbonyl compounds are sp2 hybridized. You would remember hybridization from your year one, where you have the p orbitals, X, Y, and Z mixing up to form 4 orbitals of sp3, where you have single bonds, 3 orbitals of sp2, where you have double bonds, and 2 orbitals of sp, where you have sp. That's hybridization. So anywhere you see double bond with carbon is generally an sp2 hybridization going on there. Carbon-oxygen bonds are shorter, stronger, and more polar than carbon-carbon double bond. You would have come across carbon-carbon double bonds when you, in year one, when you were talking about hydrocarbons, alkanes. Okay, so if you compare both of them, the fact that you substituted one carbon atom with an oxygen atom changes that double-double bond, because oxygen is more electronegative. And you can see the diagram here that explains that further. So we said there are 2 main kinds, the aldehydes and the ketones, and we have shown, if you look at the structures on your right-hand side, you would see the general formula that I wrote earlier. And then on your left-hand side, you will see examples. In the aldehyde, you see that the R is represented by a methyl CH3 in this particular example. Okay. We're going to shortly look at how they are named, and you can see the second example of the ketone there. In this ketone, you see that the R's are the same, CH3, CH3. But you will also see that this is more of a rarity than a commonality. That is to say that usually you have the R being different from the R prime, and that's why it is represented as R prime. Now, let's look at naming carbonyl compounds, ketones and aldehydes. You are aware that there are 2 main ways of naming compounds. One we call common nomenclature, and the other we call IUPAC. Okay, if you look at this, you will see in the bullet point there examples of formaldehyde, acetaldehyde, benzaldehyde. Those are common names. Okay, but IUPAC names, you do it systematically. Again, cast your mind back to the first time you learned about naming hydrocarbons. The same thing occurs here. You first of all identify the longest chain. The longest chain here would be the chain that has the highest number of carbon atoms, and that is also connected to the functional group. You would have that would have been explained to you previously when you dealt with alcohols, ethers, and so on and so forth. So, if you look at this, that first structure there, CH3CHO, which you can also, if you were writing it out, write it like this, CH3, C double bond O, and then H. Okay, so here you see that the R, as represented in the general formula, is CH3, and the R prime, as represented in the general formula, is H. Okay, so how do we name this? This is a bit easy because here you have just 2 carbon atoms and it's straight ahead. Okay, so first of all, you count the carbon atoms. There are 2 of them. You take your mind back to when you learned about hydrocarbons. When there are two carbon atoms, you say N is equal to 2. When N is equal to 2, what is it? Is ethane. N is equal to 1 is methane. N is equal to 2 is ethane. Don't mind my spelling. Okay? So, what you do, that's the straight chain. So, in naming this, because the R prime is H, we already know that this is aldehyde. And obviously, you can see the common name there, acetaldehyde. That's the common name. We're going to name it using the IUPAC nomenclature. So we've identified the longest chain. It has 2 carbon atoms in it. Hydrocarbon with 2 carbon atoms is ethane. So to name this, you remove the E, like you would have done. If this were alcohol, for instance, you remove the E and put OL, if you remember. So here now you remove the E and you put AL. So we'll remove the E, we'll put AL. Okay? So the name now becomes ethanol. Ethanol. Ethanol is the IUPAC nomenclature for this compound. Okay? The acetaldehyde you're seeing there is also correct, but it's the common name. So if you ask for the common name, acetaldehyde is correct. If you're asked for the IUPAC name, is ethanol. Okay? Now, you can see the next one there. It follows. It's been highlighted. Here, if you count the carbon atoms, this is 1, 2, 3. Okay? So there are 3 carbon atoms. N is equal to 3. That's propane. N is equal to 3 is propane. If you remember, this is how you spell propane, just to remind you. And then you will notice that here the E has been removed and AL has been added. And that is how you come about the IUPAC name for that. Let me quickly state here that when you count the carbon atoms in order to name, you usually start numbering them from the carbon atom that has the OH double bond. Just to note, in case we don't come across an example that so describes. Okay, so this all outline what I've just explained to you. If you have any question, can I ask that you type it into the chat section so that you can, and since I'm just telling you that. Any questions so far? Any questions so far? If you have any question, you raise up, you go click on the hand symbol there and it will show. Okay. Subsequently, we'll be breaking intermittently to take questions. So if you have any question, you either type it in the chat or you raise up your hand and I will call you at the appropriate time. Okay, so this slide explains what I've just said. You can read it later. So let's look at synthesis. Synthesis, how do we make carbonyls? How do we make aldehydes and ketones? They're usually what you call industrial methods and laboratory methods. Laboratory methods are the ones you do in the lab experimentally, but industrial are usually the ones that are done in industries. And the basic difference most times is that the industrial methods are usually cost effective because the chemist that wants to make that compound wants to make it in the cheapest way possible. so that cost of production will be less. So those of you who will go further to take courses in industrial chemistry, for instance, you will then appreciate the fact that things like availability of raw materials, ease of synthesis, cost are usually very important in this. So some of the common industrial methods of preparing carbonyls: Fischer-Tropsch synthesis. This is named after two chemists who discovered this, and it basically entails the hydrogenation of carbonyls compounds, here represented as CO plus hydrogen in the presence of coke. This coke is not Coca-Cola, is an organic compound obtained from the Earth's crust. You see latecomers just coming now, typing their names. If you can hear me anyway, those coming in will not hear me. So if you hit that in the presence of, some of you might have learned about water gas and air gas in secondary school, and this equation might jog some memories. Okay, it's called the Fischer-Tropsch synthesis, and this is how aldehydes and ketones are made. Okay, and usually you can use this to prepare the smaller molecular weight carbonyls. Oxidation of methanol using air in the presence of copper. You heat methanol, which is an alcohol, you've learnt about that, and then you get your carbonyl. Obviously, whichever you would have learnt under oxidation and reduction of alcohols, that what you get when you use a primary alcohol is different from what you get when you use a secondary or tertiary alcohol. So here you see an example of methanol, which is a primary alcohol. You expose it to these reagents, you're going to get aldehyde. So what you see here, you can write like this. You can see that in this case, your R and your R prime are the same, hydrogen. Okay, so that is the second method of making carbonyls. In this case, you're making an aldehyde by oxidation. Okay, so two methods we'll do for now. Then laboratory procedure. This is similar to the slide we just looked at, okay, except that here now, the reagents are different. So you have the general formula for the oxidation of alcohols here. Alcohol is represented by ROH. When you see a capital O encased in two square brackets, that is the symbol that represents oxidation. So when you oxidize alcohol, you will get an aldehyde or ketone. So whether you get an aldehyde or ketone depends on the type of alcohol you use. So let's look at some examples. Here in the equation, you can see that is ethanol, CH2CH5OH is ethanol. That's one way of writing it. So get used to it. You can also see it written this way: CH3, CH2OH. That's my O. Okay, so you can see that there is there are two carbon atoms here. That's why here you see C2. And if you add 3 and 5 3 and 2, you get 5, that's the CH5, and then you have your OH here. So you can either see it written as the compound circled in red, or you can see it written as the compound written in blue. So you should be conversant with either. So here, when you use potassium dichromate, you would have come across potassium dichromate even in secondary school laboratory, if you went to a good one. Usually pinkish, colorless, depending on the state of the chromium. Anyway, here, it suffices for you to know that when you subject a primary alcohol to potassium dichromate in the presence of sulfuric acid, and you warm the solution a little bit, you are going to get an aldehyde. The combination of K2Cr2O7 and H2SO4 are oxidizing your alcohol. Look at the next equation there, you will notice that that alcohol is a secondary alcohol. I'm sure Professor Adams taught you that primary alcohols are usually defined as alcohols that have the carbon that has the functional group, the OH, containing at least one carbon atom. Okay? If it contains at least 2 carbon atoms, it's secondary. If it contains 3 carbon atoms, it is tertiary. If you've forgotten that, please go look back at your slides so that you do not mix it up. So here, because I know you've been taught, you can see an example of primary alcohol giving you aldehyde and secondary alcohol giving you ketone. I'll check this quickly and see. Any questions? No questions. Okay. There's a question here. So aldehyde, again, you are not allowed to be taboing in class, but alkanals, your spelling there is not correct, but I guess I can say yes to your question. Who was that? Okay, Sade Yetunde. Yes, but the correct, what you're spelling there is not correct. So please check that. The rest are people who are probably not in class, just writing their names. Okay. Okay. Those on the live stream. If you have questions, you type it in the comments section there. We will deal with them in the next class. Okay, because we're short of time, we actually can't go down there. But if you have questions on the live stream, type it in the comment section, and then we'll get to it in the next class. Okay. So we said that oxidation of primary alcohols is one of the laboratory ways of preparing aldehydes. Now I want to specifically look at some examples. Okay, so in that first example, you saw potassium dichromate. I go back there. Now, obviously, your exam is going to be multiple choice. So, but you can, for instance, you can come across a question where you have CH2CH, that's this first equation on this slide here. CH2CH5 arrow and in the question, you will have a question mark. So in the question, this will not be there. It will be removed and you just have a question mark. And then you'll be given options A, B, C, and then you'll have to choose. Okay? So here now you're seeing that this is one of the reagent combination that you can use for oxidation. Sometimes the question might be that you're giving the primary alcohol and you're giving the reagents, but you're not giving the product. And you're asked to fill out the product. Obviously, if you don't know or if you've forgotten that the primary alcohol, when oxidized, will give you an aldehyde, then you won't know the answer. And if you don't know the answer, you cannot get the score. If you don't get the score, I'm sure you can fill out the rest. Okay, so now the next, you can also use pyridinium chlorochromate, abbreviated as PCC. If you look at the structure, the diagram there, you will see the structure of PCC is a quaternized pyridine compound, okay, with a chromate chloride counterion. Okay, don't worry yourself too much at this stage about that structure. At this stage, it just suffices for you to know that you can use this combination of PCC and to convert a primary alcohol to an aldehyde. Okay? So there are also stronger oxidizing agents that you can use on alcohols to get carboxylic acids, but that is not what we're dealing with here. Okay? So how about secondary alcohols? We've already learned that if you oxidize secondary alcohols, you will get ketones. And we have seen that you can use the potassium dichromate sulfuric acid combination to get that. Here, now we're meeting another one, sodium dichromate in acetic acid, and PCC can also be used. Okay, so you see, sometimes you'll be given, you can see these structures, they are very big. It's just to confuse you and to put fear in you. If you see it, don't be afraid. Just look for the functional group and identify the change. If the change is alcohol moving to a carbonyl, for instance, you know that is an oxidation. Okay? If the change is maybe as you would have learned in, where would you have learned that now? Okay. Let's face what is in front of us so that we don't. So here you see an example of, if you look at, it has been distinctly colored, but for those of you who refuse to see, that OH on the 5-member ring there, if you look at it there and you come and look at it at this point, you will see that the OH has become just oxygen with double bond. If you look at this, if you break it down, if you simplify it, this is, just consider that this is carbon. One bond of it has OH. The other bond of it has H. This other bond, which is here, this one here, that part, just assume that that is your R. And then this other part here, assume that that is your R prime. Okay? If you break it down like that, you will see that from this structure, it has moved to becoming this structure, where you now have your carbon that was OH before. I want to change that. carbon that had OH before now become double bond O. So if you look at this, think back to the general structures, you will agree that this is a ketone. Okay? Maybe it's okay to point out at this junction that I'm sure you already know, but you see all these structures that we are drawing here. Carbon will always have 4 bonds if it's not unsaturated. In other words, if it doesn't have a multiple bond, the maximum single bonds I can have is 4. So wherever you see carbon, and I'm sure you all know that at these vertices, you have carbon atoms there. That's to say that you have carbon atom here, you have carbon atom here, and so on and so forth. So that point, for instance, if you were to write that out, red is usually better. This point here, you have carbon, you have H, another H. Same thing here. So in some cases, once it's not written there, once there's nothing written, if you draw a stick and there's nothing at the end, you generally assume there is a methyl substituent. But if there's no stick there, you know that it's hydrogen. And if there's a stick there and there's something at the end, you know that is that thing. So just to remind you, so that in case you're confused about how we were able to recognize this as an alcohol and this as a ketone. Okay, so that's an example of how you can synthesize the carbonyl known as ketone using an oxidizing agent. Okay. Next slide. You want to look at, we've talked about, you notice that mostly is the chromate or the chromate. We've seen potassium chromate, we've seen sodium chromate as the oxidizing agents. So chromates can usually be prepared from chromic acid. So this slide looks at how chromic acid oxidizes compounds, because the chromic or the chromate moiety there or ion is usually what you call the principal actor. That is what really does the oxidation. So you can see here, this in green is the structure of chromic acid. And this slide shows you how the chromic acid converts your alcohol to a carbonyl compound. Now, apart from oxidation, you can also prepare carbonyls by reduction reactions. Excuse me. The first example we're going to be looking at here is the reduction of acid chlorides. At least you have an idea of acid chlorides from secondary school. They are generally compounds. You haven't done carbonyls here, but I mean carboxylic acid, but I think I can show you the general formula of carboxylic acids. C, R, then OH. That's the general formula of carboxylic acids. Is just like what we are learning now, we are going to find out. Instead of the R prime here being hydrogen or other aliphatic or aromatic substituents, if the R prime becomes OH, it's carboxylic acid. You will learn that in the next class. But here, it suffices us to just know that instead of the OH, if you have a halogen there, here represented as Cl chlorine, this will be the general formula for acid chlorides. Like I said, you get more information about that in the subsequent class. So, but what we are taking away from here is that if you take those acid chlorides and you subject them to a reduction protocol, if you reduce them, you are going to get a carbonyl. Again, like in the case of alcohols, the type of acid chloride that you use will determine the type of carbonyl that you get. So here, for instance, you use a reducing agent called lithium aluminum hydrogen tritertiary butoxide, also commonly called lithium aluminum hydride. Okay, you can see the structure there. Okay, if you use that, you see that this here now is an acid chloride, aromatic acid chloride. In this example, the R is a benzene ring, which is aromatic. You can also have it being alicyclic or aliphatic. Okay, so when you use lithium aluminum hydride on this benzoyl chloride, you are going to get an aldehyde. Okay, this is benzyl aldehyde. Now, I wonder, will you be able to name this using IUPAC? Think about it and let me know in the next class. What is the IUPAC name for this compound? Okay, so that's one example. Again, look at, instead of an aromatic R, you have an aliphatic R in CH3, CH2. And then, again, subjected to the same lithium aluminum hydride, you're going to get an aldehyde. This aldehyde you've come across, so I'm sure you should know the name. Where is this one? Propanol, we said. Okay. So this is another way of synthesizing carbonyls in the laboratory. I think it's self-evident, but I'm going to point it out anyway, that this method can only give you aldehydes. So whenever you reduce acid chlorides, it can only give you aldehydes. Okay, so sometimes you can get a trick question. It says the reduction of acid chlorides will give what carbonyl? If you remember that it's only one way, only one answer can be correct. So you cannot get a ketone. And obviously you can see from the structure why that is not possible. So now we want to look at ketones. Now, again, these structures here are not clear, okay? But if you take your mind back to Fidel Crafts, you were taught Fidel Crafts in year 1 FSC 112. So basically what you have here is that you are reacting. This is an acid chloride, okay, reacting with a benzene. Fidel Crafts is going to form, this is COCO2 and this is CH3. Sorry that is not clear. This one here is CH3 C double bond Cl. So you can write that out at your own leisure. This is benzene. This first one is benzene. This next one is CH3, C double bond O, and then Cl. Okay. When they react under Fidelcraft, so that means on this arrow here, you have aluminum chloride. Okay, that's what we use for Fidelcraft, if you remember. And then you will have that it will bond to the benzene ring and then give you CO double bond and CH3. So here you can see that the R is a benzene ring, which is aromatic, and the R prime is CH3, which is aliphatic. Okay, and that is how you prepare ketones. And iron bromide. Okay. Those are laboratory preparations. Now let's look at some industrial preparations. Ethanol, which is an aldehyde with 2 carbon atoms, can be prepared from alkynes. So you add water to ethyne, for instance, in the presence of sulfuric acid and mercury sulfate at 97 degrees, and you will get ethanol. Or you can also call it, it's also called acetaldehyde. Okay, the next equation there is if you use isopropanol, called isopropanol, commonly IUPAC name is 2-methyl propan 2-ol. I'm sure you'll be able to draw the structure of this. This has CH3 bonded to carbon, another CH3 here. Then that carbon that is bonded to has OH and then H. Sorry, I'm drawing rubbish there, but you get my point. So the central carbon atom has 2 methyl groups, 1 hydrogen and 1 OH bonded to it. So you can also use that to produce ketone. You need copper catalyst at 350 degrees centigrade. So those are 2 examples. One to prepare aldehyde, another one to prepare ketones. Those are industrial methods. Now let's quickly look at some of the physical properties. And as I'm sure you are aware, the physical properties are determined by the atoms in the molecule. Here, the basic difference between a ketone and aldehyde is that the aldehydes have H okay? And the ketones do not have H on the carbon that has the double bond oxygen. And that makes a great deal of difference. For instance, the polarity of carbonyl group makes aldehydes and ketones moderately polar compounds, okay? So polarity, you can see here that the carbon oxygen double bond that has a pi bond, pi electrons and a sigma bond, or sigma electrons, the pi electrons move more freely. So you can have a sort of delocalization here where the pi electrons move to the oxygen because oxygen is stronger, or to put it correctly, more electronegative. So the electrons that the carbon and oxygen are sharing in this multiple bond, because the oxygen is more electronegative, to pull it towards itself. And by pulling it towards itself, it will therefore have more electrons surrounding its nucleus. Or if you talk about it in terms of quantum mechanics, you will say that the probability of finding the shared electrons is higher in the proximal space of the nucleus of the oxygen. But don't worry about all that big grammar. It's enough for you to know that because oxygen is more electronegative, it will pull the electrons that they are sharing towards itself. It's like if you cast your mind back to those of you who did tug of war in sports in secondary school. The team that has stronger people will be the one that will pull the other team over the line and win. So here, oxygen is stronger in a manner of speaking. So it will pull the electrons towards itself. And because the electrons are closer to it, it will momentarily have excess electrons around it. And that temporary possession of excess electrons is what we denote or signify with. This is not D, it should be delta. Delta negative is a sign or a symbol, alpha, beta, gamma, delta, okay? So forgive this D that is written like this. It is delta. Okay, so because this can happen, you can therefore find a situation where the electrons are closer to the oxygen, and therefore it becomes delta negative. And because the electrons have been moved further away from the carbon becomes delta positive. Now, because he has the ability to do this, he can therefore have a dipole-dipole moment and therefore can be polarized. And if he can be polarized, it means he can be polar. And that is what polarity is all about. So if you look at your hydrocarbons, for instance, they don't have this ability. And so they are not polar. Okay, so that's one physical characteristic of carbonyls, their polarity. Okay. Now, even though they are polar, they cannot form hydrogen bond with each other. Subsequently, you're going to see, for instance, that the carboxylic acids can do this. And then I'm sure you saw that the alcohols can do this to a lesser extent. The carbonyls cannot. But they can form with other ones, again, which goes towards their polarity. You say that like dissolve like, because carbonyls, aldehydes, and ketones are polar, you find that they will easily dissolve in water because they can form hydrogen bonding. Okay, so aldehydes and ketones can form hydrogen bonding with other polar compounds like water, but they cannot form with themselves. So here are some characteristics that you can read because they are physical and they are self-explanatory. So I'll leave these ones for you. But suffice to say that things like you hear about boiling points, okay? Because these compounds are polar, it means even if it's momentarily, they can form charged entities. And if they can form charged entities, it means that they can have a stronger attractive force compared to where you just have covalent bonds. Okay? The bottom line of this is that if you compare them to other organic compounds that have similar numbers of carbon atoms or that have similar similar molecular formulas or empirical formulas, you will find out that they have higher boiling points. They are mostly liquids, no solids, so there's no melting point, higher boiling points, okay? Because of this, their ability to form partial positive and partial negative centers, okay? That increases the attractive force. So aldehydes and ketones are more polar, so have higher boiling points than comparable alkanes, you can put S there, and ethers. Okay? But if you compare them to alcohols and carboxylic acids, you find out that the opposite is the case. Alcohols, like I said, can form hydrogen bonding. So that increases their boiling points, okay, compared to the aldehydes and ketones that cannot. And as you learn, carboxylic acids are similar. Okay, so this polarity contributes to their reactivity. We've said that. And then the bond angles, because it's sp2 hybridized, it's 120. We'd have learned the bond angles, tetrahedral 109, that's sp3 hybridized. sp2 hybridized is trigonal 120, and sp hybridized linear 180. I'm sure you would have learned that. So back to aldehydes and ketones, you can read these ones. Okay, how about their reactions? Generally speaking, reactions of compounds, or rather preparations of compounds, where you say A plus B to give you C, if you turn that around, it now becomes C to give you A plus B, you will get their reactions. Okay, so what I'm saying to you basically is, it helps, if you remember the methods of preparation of compounds, then you find out that usually their reactions are the opposite of that. I think our time is almost up. So in the next class, we will look at, hold on, let me be sure. I don't want to, yeah, time is up. Don't want to exceed. So in the, today is Friday. So on Monday, we will take questions on the reactions of aldehydes and the chemical properties. So you're going to get this slide through your class reps. Please, over the weekend, look at it. On Monday, we will take questions on this, and then we will deal with carboxylic acid. Have a lovely day. Or hold on, maybe a few minutes. Any questions? Let me just quickly check. Kaka Omodele, a new MBBS student, and you're just coming to class. Well done, I just want to see if there's any question here so we can deal with it quickly. But like I said, please read the remaining parts of the slides and bring your questions. So just, you type them in. As you log on, you type them in, or those of you on the live stream, you type them there. Dr. Agubiade will pass them to me. First 5 minutes or more, depending on the number of questions on Monday, we will treat those. and then go to the next topic. It's unfortunate that we have to rush this, but you are equal to the task. Okay, have a lovely day and enjoy your week.